So here we have a rectangular swimming pool, 50 feet long, 20 feet wide, and 10 feet deep. It's filled with water to a depth of 9 feet. Use an integral to find work required to pump all the water out over the top. All right, so my goal here is to find total work. And work, according to physics, is calculated as force times distance. Force is considered a unit of pounds. Distance is considered a unit of feet. That's really important to remember your units of measure when you do these problems. So drawing my picture, I have my rectangular swimming pool whose length is 50 feet, width is 20 feet, and depth is 10 feet. Now that's without the water. We include the water in there. Don't forget that. It's pretty important. That's going to be 9 feet. So I have to think about slicing this thing because the work required to get the water from the bottom is a lot more than the work required to get the water from the top. So I need to slice this so that the amount of work to move that water is approximately the same. So if I do that, that means I'm going to slice it horizontally. And think about that slice in general right there. So I pull that slice out. It's going to look like a skinny box or a stick of gum. Now, no matter where I slice this thing, the slice is going to be approximately the same. It's going to be 50 feet lengths, 20 feet wide, and if I make it real thin, it's going to be delta H, thick. H is being for its height, where it is in the pool, where I slice it. All right, that's really good. So let's see, let's calculate. We need to calculate the force on my slice. And we have to calculate the distance the slice moves. So we remember with water, we know that water weighs 62.4 pounds per cubic foot. And we have to think about what we're going to multiply this by to end up with pounds in the end. That's what we want, pounds in the end. So I have to multiply it by something that's cubic foot, and the only thing in the world that's cubic feet is volume. So the volume of my slice times the density of the liquid in there, and this is true, by the way, all the time for force. The density for whatever you have in there times whatever unit of measure is down here is what's going to actually give you the force that you want. So sometimes this is square foot or just foot, but in our case, due to the structure of the problem, this is pounds per cubic feet. All right, now, so if I want the force of my slice, I have to have the volume of my slice. The volume of my slice, that's just a box, so that's length times width times height. So every slice will have the same length of 50 feet, will have the same width of 20 feet, and the same thickness, delta H. So that's a little straightforward. It's kind of nice when something's straightforward in mathematics. So if I continue, I don't want to cram this all in here, but I'll try it again down here. The force of my slice is going to be 62.4 times 1,000 delta H. Now I have to think about the distance of my slice that the slice has to travel. So there's two cases that you can go through. You can have case one, where you think about your slice as being coming down from the top. That's how deep it is. It's H units deep. Or you can have case two, where you measure your slice from the bottom. I don't care which one you do. You just pick one. There was a student in my class that says, I'm going to measure everything down from the top. You do that, and it makes things a lot easier for yourself. You still have to think about stuff, but you start thinking about the same problems very consistently. And always mark your H's. Always mark where you're measuring things from in all these problems. Not just for the reader, but for you when you have to go and think about the boundaries of your integration. All right, so if I think about case one, I'm going to put a line right down here. If I think about case one, I have to think about the distance that this slice has to move to get to the top. So if I think about that carefully, that no matter where my slice is, if I keep measuring that slice from the top, the distance it has to travel is h. That's nice, straightforward. Now this one over here is a little bit different. If I think about how far that guy has to go to get to the top, well, I know that this length is 10, and I know then that the distance that it has to travel is this far, which is 10 minus h. So the distance of my slice here is 10 minus h. So then putting it all together, work on my slice is equal to force 62400 times h times delta h. Force times distance. Same thing here. Work on my slice is equal to force times distance. Now, 2, depending on which case you choose, depends on the limits of your integral. So if I integrate here, I'm just going to fill this in, 62400 h delta dh, excuse me. We're integrating here. I'm going to add up the work on all these slices, 62400, 10 minus h dh. But now the limits are going to be different based on this. So if my slice is clear at the top, my h is no depth, so it's 0. If my slice is at the very bottom and I have to move it, h is going to be 10. But we forgot about something here. We got to remember that the water is only at depth 9 feet. So the very top slice is right here at h equals 1. So which limits do I use? Do I go from 0 to 10, 1 to 10? Well, because my very top slice is going to be here at the top of the water, and it has to move 1 foot, and h is going to be 1 there. So my lower limit is going to be 1. My upper limit is going to be 10. The difference on this one, if my slice, let's remember the water this time, if my slice is at the very top right here, that means my h is this long right here, and that's 9. So at the top, h is 9. And my slice at the very bottom, when moving it, the distance it is off the bottom, which is what my h is measuring, is 0. So my limits here are going to be 0 to 9. So notice, even though there's different integrands here, the limits will take care of it. And these outputs should be exactly the same. That's how you know, let's say your friend did it this way and you do it this way. If your answers aren't the same, then somebody made a mistake. When you do calculate these, which are very straightforward integrals to calculate, you should end up with 3088800 units of work. Now, what should I call my units here? Well, we discussed that at the beginning. Work is going to be foot-pounds. So in this case, then we're going to write foot-pounds. And we are done.